In this example, we will consider a non-trivial example of rotational motion applied with kinetic energy. In the diagram below, m1 equals 15 kilograms, m2 equals 20 kilograms, and m3 equals 20 kilograms again, and r is equals 0.5 meters. How fast is m2 moving if it falls 1 meter from its initial position? So let's take a look at this diagram carefully. So this is going to be 15 kilograms. This is going to be 20 kilograms for M3, and this is going to also be 20 kilograms. And R here is 0.5 meters. Okay, so what we want to do is ask how fast M2 is moving as it falls 1 meter from its initial position. So this is an energy conservation problem, so let's just consider that. Let's just consider this thing at y equals 0 here. Okay. We're just going to look at changes actually in VAC. So this is actually going to be a little easier than it seems to be at first. Anyway, so let's look at the initial state. Okay, so initial state is kinetic energy is equal to 1 half m1v1 squared plus 1 half m2v2 squared plus 1 half I2 m3v3 squared I2 omega 2 squared. All right. Now let's just write down what I2 is going to look like. I2 is going to look like 1 half for a solid disk m2 r squared. All right. So I really like this basically is because I want to choose my axis in such a way that this will make sense. But initially this actually is fine because nothing is moving, and so in fact all these three values will be 0. So in fact the kinetic energy initially is equal to 0. All right. Now the potential energy we can also pick just as easily. All right. If I pick this to be well, I'll just pick this to be y equals 0 initially. All right. Okay. So in that case, this is potential energy. There will be two sources. There will be m1 and m3. So it will be basically m1gy1 plus m2gy2. All right, and I will just set this to be 0 initially. All right, you'll see how I can get away with this in a second. Anyway, once we have this, what this means is the mechanical energy initially is going to be equal to the kinetic energy plus the potential energy initially, which is now equal to 0. All right, so that doesn't seem like I've gotten very far. Right, let's look at the final state. All right, the final state is if this thing has moved down about 1 meter and this object has moved up about 1 meter. All right. Okay. So let's consider the kinetic energy first. So the potential energy, it's the potential energy first. The potential energy in the final state is going to be m1 g y1 final plus m2 g y2 final. All right. Okay. Now, relative to what was started out initially, y1 final is equal to y1 initial plus, let's say, 1 meter, because this thing has risen 1 meter, and y2 final is equal to y2 initial minus 1 meter, because it has fallen 1 meter. So I'm going to take this and plug it in here. This will just give me m1g y1 initial plus m1g times 1, that's plug it out in that part, plus m2g y2 initial minus m2g times 1. Right? Now this is the same as that, which we've set equal to 0, right? So this plus this is equal to 0. And so we're left with the potential energy of the final state to be equal to something very nice, which is just basically m1g times 1 minus m2g times 1, which is just simply going to be, I picked the wrong one. This should be 3, 3, 3, times 3, right? M3G minus 1, which is going to be equal to M1 minus M3 times G times 1. Okay, so we're going to use this result in a second. Why? Because now we can write down the kinetic energy. All right, so the kinetic energy, okay, is going to be equal to, now we have to choose this carefully. Now, there are many different ways of choosing this. In this case, I'm going to basically choose the y-axis to be this way. Right? It doesn't really matter. Well, let me just show it to you again. That's the y-axis pointing straight outward. Okay. So in that case, basically we have basically 1/2 m1 times v1. Right. Now, there's going to be an overall v, I guess. Right. So if that's pointing that one, then basically I have that v1 is equal to v, right, whatever that v is. V3 is equal to minus v because this is falling, which is good in terms of v. And then in that case, if I want omega to be rotating positive counterclockwise, right, then as v is moving upward in this direction, it will move it clockwise. So this will be negative again. So in that case, this omega 2 is equal to minus v over r. Okay, I will use these results in a second. It turns out not to be very important because the minus signs will be killed by the fact that everything is a square. That's the beauty of using energy conservation. You don't have to worry about this sort of stuff. Okay, so 1/2 m1 v1 squared plus 1/2 m3 v3 squared plus, now what is I2? 1/2 of 1/2 m2 r squared omega 2 squared, right? So if you plug everything in, all these terms in, you're going to get something that looks like 1/2 m1v squared plus 1/2 m3v squared. Okay, the minus ones will be killed by the square. Plus, now this is going to be 1/4. R squared times omega 2 squared is going to be minus v squared, but minus v squared is just v squared. m2v squared, right? So what this ends up giving you is something actually very nice and simple. All right. We'll set this equal to where is it? The potential energy, which is right here. Okay, so this is going to be equal to, well, this is negative that, so that's whatever this is. So let's just write this thing down. Be 1/2 of what? So this is going to be 15 kilograms plus 1/2 of 20 kilograms plus 1/4 of 20 kilograms v squared, which is what I want to find, okay, plus, okay, right. So the mechanical energy is the kinetic energy plus the potential energy. Well, what's this going to be? Well, so this is actually going to be this entire thing here, which is 22.5, right, v squared plus this term, which is going to be 15 minus 20 times g, 9.8 times 1. All right. Okay, which gives me something very simple. This term right here is minus 5 times 9.8. That's about 49 times 1, which is then now to 22.5 v squared minus 49. Right. So solving for this gives me v squared is equal to 49 over 22.5, which is equal to what? Let's bring out a trusty calculator here. 49 divided by 22.5 is basically 2.1. Let's take the square root of that, and that gives me that v is equal to 1.5 meters per second. Right? Well, hope that was helpful.